We are seeing optical communication, and here we are going to see about the photodetectors. Semiconductor photodetectors work on the principle of internal photoelectric effect. The excess carriers on and above the existing thermally generated carriers are called photogenerated carriers. So these will appear in the external circuit in the form of photocurrent or photovoltage. There are different types of photodetectors. There can be bulk or junction photodetectors based on the internal mechanism for multiplying the photogenerated carriers. We have pin detector and avalanche photodiode. Depending on whether the energy of the observed photon is close to the band gap or much less than that, photodetectors are further classified into intrinsic and extrinsic categories. What are the characteristics of photodetectors is the size compatibility we have to see, then the high conversion efficiency we have to see, the high sensitivity at operating wavelength, then its high response speed, and it should have very minimum noise. Based on the internal mechanism for multiplying the photogenerated carriers, in the non-multiplying case we have pin photodetector. In the multiplying photodetectors we have avalanche photodiode. So in these photodetectors we have to find the quantum efficiency. So what is the quantum efficiency of a photodetector? It can be found using this formula: eta is equal to IP divided by Q divided by pi in, the input power P in divided by H nu, where IP is the photocurrent, Q is the electronic charge, P in is the incident optical power, and H is the Planck's constant, and V is the frequency of incident light. So if we find the alpha, the optical absorption coefficient, we can write the equation as IP is equal to Q divided by H nu, P in into 1 minus e power minus alpha W into 1 minus RF. RF is nothing but the Fresnel reflection coefficient. So the value of eta should be less than unity, and it is usually expressed in terms of percentage quantum efficiency. Diffusion, we have seen diffusion current density. Now the drift current density is given by the formula J suffix dr is equal to IP by A. So A is nothing but the photodiode area, phi naught is the incident photon flux per unit area. Then they are finding the whole diffusion. So the whole diffusion can be determined by the one-dimensional diffusion equation given by this formula. So dP is nothing but the whole diffusion current, Pn is the whole concentration in the n-type material, and tau P is the excess whole lifetime. Pn naught is the equilibrium hole density, and G of x is the electron hole generation rate, given by G of x is equal to phi naught alpha s into e power minus alpha into x. So by finding the diffusion carriers, we can find the junction capacitance, which is equal to epsilon s A by W. So from this we can find the DC, which is equal to 1 by 2 pi RT CT. CT is the total capacitance. Then we can find the signal to noise ratio given by this formula: I square P M square divided by 2Q IP plus ID into M square F of M into B naught plus 2Q IL into B naught plus 4K GB divided by RL. Then the dark current and thermal noise current are given by this formula. So the mean square dark current, the mean square thermal noise current. So just we have to substitute the values and find the current. Then some of the problems we are discussing here. So in the first problem, they are asking the cutoff wavelength of the device. So the energy, band gap energy, they have given as 1.43 electron volt at 300 Kelvin. So cutoff wavelength is nothing but Hc by Eg. So we will find the wavelength. In the second problem, they have asked the quantum efficiency. So here they have given the number of electron hole pairs generated, and we know the photons, incident photons, number of incident photons value. So the quantum efficiency we can find. In this problem, they have given the energy and the responsivity. So the optical power they have given as 10 microwatt. What is the? We have to find the photocurrent generated. In the next problem, they are asking the primary photocurrent. So quantum efficiency they have given, wavelength they have given, the input optical power they have given, photocurrent also they have given. They are asking here the multiplication factor m. So they are finding Im divided by Ip. In this problem, they are asking the various noise terms at the receiver. So they are first finding the primary current, next the mean square short noise current for a fin photodiode. So Ip is equal to responsivity into Pn. The mean square short noise current for a fin photodiode is given by 2q Ip into bandwidth. In this problem, they have given the capacitance value, photodiode capacitance, amplifier capacitance, both value they have given, the load resistance value they have given, the amplifier input resistance they have given. We have to find the bandwidth. In the next problem, we have to find the 3 dB bandwidth of the photodetector. So F is equal to 0.4 into V divided by W. So 0.4 into 10 power 5 minus 5 into 10 power minus 6, which gives the frequency 8 Hz. In this question, here also they are asking to find the bandwidth of the photodetector circuit. And in the last problem, they are asking the dark current value, SNR value, so they are asking to compare the avalanche photodiode with the fin photodiode. So first they are finding the multiplication factor, then the SNR value. So for a fin photodiode with the multiplication factor m is equal to 1, the SNR value they are finding. So what conclusion they are making is, compared to a fin photodiode, the avalanche photodiode improves the signal to noise ratio by 24 points.